Good morning, everybody. Welcome. Thanks for turning out. We got an early start. We're going to kick this off. So I am Caleb Lusk, one of the project leads for Rack and Power, and
so I'm Steve Mills. I'm the other project lead for Rack and Power. I'm a mechanical engineer at Facebook.
I'm also a mechanical engineer at Rittal. So if you guys, there's a lot of familiar faces out there. Some of you we don't know. If there is anybody that wants to know more about Rack and Power or OCP in general, feel free to find Steve and myself either throughout the workshops or out in the sessions later today. So we can definitely hook you up. And again, welcome. So it's all yours.
All right,
if you guys want to go ahead and introduce yourself.
Yeah, can you hear me? So welcome everybody. Thanks for coming this early morning. I'm Brandon Rubenstein. I'm a manager for the mechanical and power team for the server group at Microsoft.
And I'm Shaun Harris. I manage the power team in Microsoft, and I'm going to let Brandon take the first half of the presentation, and I'll take the end.
We have kind of a tag team going on this morning. So this is kind of an exciting topic this morning for us because, well, I'll get into it. This is Shaun and I. So what we're trying to do is combine the two open source platforms within Open Compute, which is Project Olympus and the OpenRack. So we're exploring the avenues that are involved with combining the two platforms. So we'll look at it from an Olympus standpoint and Olympus's adaptation to OpenRack. So some of the points of Project Olympus that we find valuable, we built Project Olympus around a building block architecture. So we have modularity. We also have the ability to kind of combine the building blocks together as we need them. So that's proven very useful to us so far. The versatility as well. Several CPU architectures within that one building block, so we've been able to adapt different vendors, CPU architectures into this same chassis. We've developed two storage platforms, so we have the Flash platform and the JBOD platform also on Olympus. And we've been able to do new infrastructure solutions, so variations to building blocks, and all these things can go together, and they're adaptable to whatever specific need we have for our specific cloud business. But there's always room for improvement. So the goal of this investigation was to expand the Olympus building block portfolio into OpenRack. So we're basically taking those building blocks that we've developed for the Olympus infrastructure and looking at the OpenRack infrastructure and combining the two just to make Olympus more valuable, more versatile, more useful to a wider audience. So basically that opens up Olympus to these new power infrastructures, the new form factor infrastructure that is available in OpenRack. And also, obviously, for the open community, we have interest in hardware convergence, and this is kind of what that enables. Part of that hardware convergence is there's always innovation going on both platforms. When we're combining that innovation, we can better adapt that innovation as far as networking, liquid cooling, I/O innovations. We can combine that effort and hopefully turn out a better product. And obviously the last bullet there, drive cost through added volume. So the major points that Olympus gains by moving over to OpenRack. So the power distribution of OpenRack, and Shaun will go into a lot more detail on this, is kind of one of the major differentiators between today's Olympus and OpenRack, the power shelf solution, the pooled power. We also have the opportunity to reduce server weight by moving that power supply out of the server, which is the way OpenRack works. Mechanically, we get a benefit out of OpenRack by widening that platform. So we move to the 21-inch versus the 19-inch platform, and we gain ourselves space for an expansion slot. That front panel space is very valuable, of course, because that's where the I/O lives, and so it gives us more I/O space or room for batteries or such things. Any kind of liquid cooling innovation that goes on in OpenRack makes adaptation very easy for Olympus as well. And then here I'm just stating the things that stay with the Olympus form factor. So the motherboard, expansion cards, all the basic building blocks are still Olympus. And then importantly, the management infrastructure stays Olympus. So everything that we've done around health monitoring and power control and all the things that we've put into our management infrastructure stays. And then we move, we can stay with RU, we could potentially go to OU. That's the flexibility of OpenRack. A couple of points here before we move into Shaun's part of the presentation. This is not a discontinuation of the Olympus infrastructure. So this is an expansion of Olympus, but not an abandonment of the PMDU and the Olympus infrastructure. It's just an expansion. So we're continuing to develop and innovate with the Olympus infrastructure. There is a couple of examples out on the floor of this new model. So we have a server blade on our stand, and then Quanta built an Olympus in OpenRack, and they're showing that here too. And then there's the OpenRack V3 specification that's coming from Facebook. Okay, here's Shaun's.
And now about power and voltage. Real quickly, like Brandon said, we're expanding the portfolio. We're looking at moving to a 48-volt distribution. But fundamentally, we're going to look at efficiency, low cost, reliability, availability, those factors for the next platform. Really simple questions. What's best? That's a hard question because how do you measure what's best? Do not read this. This is just a list of worldwide legislation that's really pushing us to higher and higher efficiency. And there's holes in the specs. You can game the specs, but why would we? I believe efficiency is king. The next system should be focused on efficiency because efficiency is the most important thing when it comes to power other than providing the proper voltage and energy. Efficiency directly hits the bottom line. When we look at a cost per watt, I get this question a lot from mostly my managers. What does a watt cost us? And people think, well, it's 2 cents a watt, it's 4 cents a watt, 6 cents a watt, because that's what we pay in our electric bill. That's not the case. The reality is, when you lease a colo space, it's the CapEx to build, the foundation, the OpEx to operate the building, the water, the electric, the personnel, the taxes. All that's rolled into it. Then the profit that the colo provider is going to provide you. So all that adds to the basic electric cost. If you look at this graph, I've made some guesstimates here on what an equivalent penny per kilowatt hour would be. And a lot of this depends on where you are in the world, your tax structure, the feature set delivered and purchased in that colo. But on the low end, you're at 10 cents per kilowatt hour. That's not too far above what some people pay in the home. So that's a pretty low price. That's a pretty slimmed down design. On the right-hand side, you've got the more feature set, dual cords, highly available 5 nines type data center. And that's pushing 40 cents per kilowatt hour in my best guess. So if you look at that charge per watt per footprint, and if you back up 10 years, colo providers didn't charge by power, they charged by rack footprint. And then over the decades, we saw rack power go higher and higher so they could reduce the cost charged back for that footprint. Well, colo providers realized that's not a good way to be profitable, so they changed it to how much power is allocated. So again, this goes back to the importance of efficiency. If you go through the math, it really doesn't matter what power per rack you deploy, whether it's 10 kilowatts or whether it's 20 kilowatts. You're going to be charged the same amount of charge back. And if you look at that charge back per kilowatt hour, per kilowatt month, per kilowatt year, over 4 years, a 10 kilowatt rack could cost you $34,000 just for that rent spot on the low end. On the high end, that 10 kilowatt could be 138. 28 kilowatts, nearly $500,000. 300 what? Nearly $400,000, 387. So $1 per watt to me is somewhere between $3 and $13. So efficiency is king. Let's talk about the different voltages. I know we've been talking a lot about 48 volts as being the best thing since sliced bread. It's going to save everybody. I'm going to tell you all of these work. All of these have advantages and disadvantages. I personally have built and delivered all three of these topologies in my career. So it happens. I mean, it's going to come down to plus or minus 0.5%, and it's really going to depend on how you use it. If we look at distribution bus bars, I mean, it's IR losses. The higher the voltage, the lower the current, the lower the losses. In Mount Olympus, we've done a VAC distribution, and that is the bottom row on the graph. I'm using that as a baseline to translate this to a equivalent at 48. You need 17 more times copper. To translate that to a 12 volts, it's what? 271 times more copper. So you really don't want to do 12 volts at 17 kilowatts. That's the takeaway. I would venture to say that 48 volts is manageable. Copper's not that expensive. We can manage that cost if there's efficiency advantage. And let's talk about efficiency. I think there's been tremendous breakthroughs in the topologies of 48 to 12 volts over the last 5 years. Prior to that, we were looking at fixed duty cycle converters, hovering around 96.6% efficiency. Very good, well thought out design. We're seeing advances in other topologies, the STC design. I'm seeing promises of 99% efficiency. And if that holds true, that does change the game. That does push 48 volt to get a 1% better efficiency. But right now, it's all demo type stuff, and I'm a skeptic. You got to show me for me to believe it. I got to measure it in my lab to make sure that I'm not missing anything and I've got something that has been overpromised. So I've got on my left side top graph, I've got a promised and a measured for AC to 48, and a promised and a measured for 48 to 12. And if you combine those two net on the right-hand graph, you're looking at a best case of 96.6, 90 down to what, a little bit over 95. So that's what I think is what we can expect out of the 48 volt distribution. Now, if we look at that and compare it to what we can get best in class for AC to 12 volts today, it's about the same. So I don't see a terrific advantage here. So in distribution voltage and conversion efficiency, I think it's about the same. There's not a clear advantage. But let's talk about the requirements and how you use it. So this goes back to the business. The V2 was predominantly a single cord N+1 design. Microsoft does have that product in our portfolio, but the majority of it is dual corded 5 nines, high availability, customer cloud facing products. We need something a little bit different. So we see different form factor or different cost points. We have requirements put onto us by the data center. For dual cords, the cords have to be balanced. They're all 3-phase power. All 3 phases must be balanced. We also deploy at different power levels per rack. Right now it's 10, 14, 17. We're on the cusp of plus 17, 20, 24, 28, 34. That's what we have in our portfolio. So we have a wide range of rack power we have to deploy. We also have a wide range of chassis we deploy. We could be down to 300 watts per U. Next generation probably is 700, 800 watts per U. On the horizon is 1200 watts per U. And it really doesn't matter if it's a single core or a dual core. If you got a dual core chassis, Well, it takes up that power. If you've got a single core chassis, well, you put 2 of them per U. So it is still the same power per U envelope. Let's see what else. How am I doing on time? 4 minutes. I'm doing great. I'm actually ahead of schedule. The problem that we see with PowerShelf, going with dual cords, is you have to forward in increments of 3 to meet the data center requirements. So you're at 3 plus 3, 6 plus 6, 9 plus 9. And so you see these jumps in cost and power capability. So if you have a deployment that's just over the limit and you need that next shelf, well, your costs go up. Your metric of what is going on here? There we go. Your metric of cost per chassis. On the left-hand side, we have CapEx per rack. And when the horizontal bars, the step loads of the horizontal bars represents every increment that you have to increase and add another power shelf. Now this is very simplified. This does not include distribution. It does not include power cords, connectors, or anything. This is just an apples to apples comparison of what we're facing. The rising lines represent what we see in Olympus. If you want 36 blades per rack, you're going to have just 36 blades per, or 36 power supplies per. So it's pretty constant depending on how you use it. You do see 2 lines here on the rising axis. The green line represents a chassis that is running closer to the maximum. So we see a highly optimized dollar per watt type application. The blue line represents that 300 watts per U. And it really does not work well, and that's a little bit painful for us. The blue line is a dual cord. The yellow mustard colored line is a single cord. Then you can look at it on a dollar per watt for this, just the same numbers, just a different representation, dollar per watt. And you can see of how you use it will determine what is best from a cost perspective. Okay, so to summarize this, everything works. There's nothing that's wrong here. 48 volts holds some promise. We're seeing some really good things. And if we can really hit 99% efficiency at 48 to 12, I think that's a game changer. Otherwise, it's going to come down to the business and how we're going to use it. Single cord, dual cord, 300 watts per U, 800, 1200 watts per U, just things that we don't know what's coming in the next 2 years. So, there we go. So, to sum up, we are adding the OCP V3 to our portfolio. It's going to be in companion with what we're doing for Mount Olympus. We've done this proof of concept with V2. You can go over to the booth and see that now. And then we've got the specifications out there. That's a wrap. Did I hit time? I got a minute left. Are there any questions? Come on, there's got to be a question somewhere out there.
If we do have questions, if you don't mind, there are 2 mics here in the middle. If you can just jump up, or we'll pass a microphone around as well. These are being recorded, so we want to be able to track the questions.
You talked about N plus N and increments of 3 per power supply, but there are solutions with ATS that can be configured at N plus 1. Have you looked at that?
The problem that I understand with N plus 1, with an ATS on the power supply, is the power cords would be imbalanced. And I have a requirement for my data center that the power cords be roughly balanced at all times. That feeds back to how the load would be transitioned in case of an AC failure upstream. So it does work, but it takes some finesse.
Question on, you're trying to replace existing architecture that takes an input voltage of 12 volts. Have you looked at other opportunities where you're feeding 48 directly into the server and there's a 48 volt distribution on the motherboard and other equipment?
We have, and I think that works. You know, it's just going to come down to what does it really cost? Does it really give us efficiency advantage? Does it give the portfolio flexibility? But yeah, there's some great things. I'm loving what I'm seeing in the industry. I think we're gone. Thank you.